In this unit, we are going to be talking about chemical equilibrium. And equilibrium is actually not a new term for us. We've actually looked at it in two previous units. We looked at it in the gas unit when we were talking about evaporation. When the rate at which molecules leave the liquid form to become gases equals the rate at which gases then reform to become liquids, you have reached a state of dynamic equilibrium, meaning the two rates of the opposing processes are equal. We also looked at it when we were in the solution unit, specifically when you have a high concentration of solute that has been dissolved, you will reach the point at which your solution is now saturated, meaning if you add any more solute, no more will dissolve. And the reason why was because if you have enough solute that has dissolved into its ions, then that increases the probability that those ions will strike the solid and crystallize. So at that point, the rate at which ions are being formed by dissolving equals the rate at which solids are reformed by crystallization. Those are two opposite processes. So when the rate of them are equal, you are in a state of dynamic equilibrium. So in this unit, we're going to be looking at equilibrium, but specifically for chemical reactions. So we call that chemical equilibrium. So again, chemical equilibrium occurs when opposing reactions are proceeding at equal rates. Now, the important thing for you to know specifically for chemical reactions is it's when the rate at which the products are formed from the reactants, so that's the forward reaction, equals the rate at which the reactants are formed from the products. So that would be the opposite process, that would be the reverse reaction. So those two are equal. When they are equal, you are in chemical equilibrium. So there are two requirements for equilibrium to occur. The first one is that the concentrations of the reactants and the products can no longer change with time. The important thing to keep in mind is the fact that the reaction is still occurring, you just don't see any change in concentration. That's why we call it dynamic equilibrium. The second is that neither the reactants nor the products can escape from the system. If those two conditions are met, you're in equilibrium. So if you look here at these two graphs, at A, what this is showing you is that at time equals 0, you have N2O4, but you have no NO2. So what that tells me is that N2O4 can either be my reactant or my product. And what this graph is showing me is that even though I don't start off with any NO2, I will eventually reach equilibrium. And after that dotted line, what you should notice, since your y-axis is concentration, yeah, they're not equal. Your concentrations don't have to be equal to be in equilibrium, but notice they are not changing concentration. So after equilibrium has been reached, the concentration of NO2 and N2O4 do not change. For B, what this is showing you, notice the y-axis is rate. And so at this point, notice that the rate at which N2O4 disappears and NO2 forms after equilibrium has been achieved, those rates are equal. Here what this is showing you, these two graphs show you that it doesn't matter whether or not you start with your reactants or your products, you can still reach equilibrium. So the graph on the left-hand side shows you that you start with your reactants, H2 and N2, and NH3 is your product. So you start with just your reactants, but you're still able to reach equilibrium because the concentration of NH3 increases until you reach equilibrium. Notice it's equilibrium because the concentration of those three substances do not change. For the second graph on the right-hand side, notice I start with what I would consider typically my product, and I start with no reactant, and yet I still reach that same equilibrium. So it doesn't matter what you start with, as long as you provide your reaction with the conditions, a closed system, necessary for equilibrium to be established, equilibrium will be established. So now that we've talked about chemical equilibrium qualitatively, let's talk about it quantitatively. So what I have right here is just a generic reaction. Keep in mind that the lowercase letters represent your coefficients while your uppercase letters represent your substances. And I have this double arrow, and that represents the fact that that reaction reaches chemical equilibrium. So the law of mass action actually expresses the relationship between the concentrations of reactants and of the products once you have reached equilibrium. So specifically, the equilibrium constant expression, that demonstrates the relationship as expressed by the law of mass action. So specifically what you do is you say the constant, your equilibrium constant, which is your Kc, that equals the concentration of your product, D, raised to its coefficient times the concentration of E raised to its coefficient divided by, and then the same thing but this time with the reactant. So notice your products are in the numerator while your reactants are in the denominator. So what this table is showing you is a bunch of different experiments in which I start with different concentrations of N2O4 and NO2. N2O4 is my reactant and NO2 is my product. So notice for experiment 1, I start with no N2O4 but a little bit of NO2. The next one still no N2O4 but a little bit more of NO2, and you can see how all of these are very different. What you should notice though, yes, the concentration that they reach when they're in equilibrium are different, but look at their equilibrium constants. They're all the same. And so what this demonstrates to you is that no matter how much reactant or how much product you start with, once these reactions reach equilibrium, and you can actually calculate their equilibrium constant, at the same temperature, the equilibrium constant will stay the same. If you change temperature, then the equilibrium constant will change, but otherwise it will stay constant. Up until this point, we've been talking about the equilibrium constant and the equilibrium constant expression in terms of concentration. Well, we can actually also write this in terms of pressure when we're dealing with gases. And so this is actually how we would write the equilibrium constant expression for pressure. It's your Kp. Kp is your equilibrium constant now. And now you just use partial pressures rather than concentrations. So this is extremely similar to the equilibrium constant expression for concentration. Now, let's actually look at an example in which we're calculating our equilibrium constant. And 3 things for you to keep in mind. The first is that your equilibrium constant depends on the stoichiometry now, not the mechanism. And so we'll be using the coefficients from the reaction. Secondly, the expression is only valid for gases in aqueous solutions. So therefore, if you have a solid or a pure liquid, you are not going to include it in your equilibrium expression. So let's look at an example. Here it gives you your equilibrium reaction and it asks you to write the equilibrium expression. So remember your equilibrium constant, and here I'm going to be using concentration. It could be pressure, but I look at B and see that we're talking concentration. That equals the concentration of H2 raised to the 4th. I'm not going to include iron oxide because it is a solid. So I'm going to put the concentration of hydrogen gas raised to the 4th over, well, for my reactants, the only reactant that I'll use in my equilibrium expression is going to be water. So it's going to be water raised to the 4th. Okay, so now it asks me to find the equilibrium constant when I have 0.1 molar of water and 0.2 molar of hydrogen gas. And so my Kc is going to be equal to, well, 0.2 is the concentration of H2, so 0.2 raised to the 4th divided by 0.1 raised to the 4th. And so my Kc is going to be 16. So that's all there is to it. So in this lesson, we're actually going to learn how to interpret the equilibrium constant to understand what exactly it tells us about the equilibrium reaction. And then we're also going to learn how to work with the equilibrium constants, specifically learning how to manipulate them in order to study the reactions that we're concerned with. So first of all, let's talk about the magnitude of equilibrium constants. Well, if your equilibrium constant is a lot larger than 1, what that tells you is that the equilibrium lies to the right. And since your numerator represents the products, that means that you have more product being formed than reactant. So what we say is that you can either say the equilibrium lies to the right or simply that the products are favored in the equilibrium reaction. If your equilibrium constant is less than 1, what that tells you is that the equilibrium lies to the left, meaning that your reactants are favored because remember again, reactants are in the denominator, and therefore if your K is less than 1, that means that the denominator value is larger than the numerator value. Now that we've talked about the quantitative value of your equilibrium constant and what that tells you about whether your products or your reactants are favored, I'm now going to show you ways in which you can manipulate equations and therefore how to manipulate your equilibrium constant. So this is the Haber process, nitrogen reacting with hydrogen to form ammonia. And the first question in A simply asks you whether products or reactants are favored. So let's review how you determine that. Well, first I have to actually calculate my equilibrium constant. So I know that my Kc, my equilibrium constant, equals my concentration of NH3 squared all over my concentration of N2 times my concentration of H2. And I'm going to cube that. Now I'm just going to plug in my values because I know all of my different concentrations. So into this, for the concentration of NH3, I have 2.1 times 10 to the negative second. I'm going to square that all over the concentration of N2, which is 8.5 times 10 to the negative first, times the concentration of H2, which is 3.1 times 10 to the negative third, and I need to take that value and I need to cube that. And so what I end up getting for my Kc is that it equals 17,415. Okay, so I'm going to round this to the correct number of sig figs. I'm going to just say 17,000 is what my Kc equals. Now, since this is much larger than 1, what that tells me is that the concentration of products, of what has been produced by products, is much greater than for the reactants, which means that my products are what are being favored in this equilibrium reaction. Right? Now let's actually see how I can manipulate this Haber cycle process, this reaction, and what I need to do in order to calculate my equilibrium constant as a result. So if you look at B, what you should notice is that this reaction right here is just the exact opposite of the reaction I had above. So my Kc for this is going to be equal to the concentration of N2, because that's now my product, times the concentration of H2. That's going to be cubed all over the concentration of NH3, and that is going to be squared. Now what you should notice, this versus this, well, how does my Kc here compare to my Kc here? Well, this Kc, to get this equal to this, all I need to do to my Kc and to this is just flip it. So my Kc, this is actually just going to be equal to 1 over this Kc will give me this equilibrium constant. So what that tells me is if I flip a reaction, what you have to do to the equilibrium constant, you just have to find the reciprocal of it. You have to flip it as well. So if you flip a reaction, then the equilibrium constant, so the Kc, is going to be equal to just the reciprocal. Because all you have to do to get the original equilibrium constant is flip this reaction, so that's all you got to do to your Kc. Now, let's look at what happens if, notice here, all I've done is I've multiplied all of my coefficients by 2. That's the only way it's different from A. So if I find my Kc of this guy, I know that this is going to be equal to NH3, instead of squared now, it's going to be raised to the 4th, and then this is going to be N2 squared, and then this is going to be H2 to the 6th. And so if I want to get this equilibrium expression looking like what it did in A, what I could actually do is take NH3, square it, all over just your N2 times your H2 cubed, but then take the entire expression and square it, because then I would get NH3 to the 4th, N2 squared, and H2 to the 6th. So what I'm going to end up doing to my equilibrium constant is I'm going to raise it to whatever value I multiplied my entire reaction by. So you're going to raise it to the number that multiplied reaction by. Now, I'm going to go over this again at the very end of this video. But there are just two ways that I can manipulate a reaction. Let's now look at another example, but in this case, I'm not just going to be flipping reactions or multiplying them by a constant. I'm actually going to be adding up reactions, just like I did with Hess's law. All right, so if you look at this example right here, it gives you the reaction. Oxygen reacts with oxygen to form ozone. And then it actually gives you just two different reactions with your KEQ. So this should bring up memories of Hess's law quite a bit. What I want to do is I want to sum these two reactions together in order to get this final reaction, which is exactly what I did with Hess's law, except now I'm dealing with my equilibrium constant. All right, well, I want oxygen with the monatomic oxygen on my right-hand side, on my reactant side. So what that tells me is that I'm actually going to want to flip this reaction above. So I'm going to flip it quickly. And so in order to flip it, remember, when you flip a reaction, the equilibrium constant, you just need to find the reciprocal of that. So I'm going to take 1 and I'm going to divide it by 6.8 times 10 to the negative 49th, and I end up getting 1.5 or 1.47 times 10 to the 48th. Okay. Now, if you look here, I want O3 on my product side, so I'm going to also have to flip this reaction. So I'm going to do NO2 reacts with oxygen, and it forms O3 and NO. All right, so since I flipped this reaction, what that tells me that I need to do is I also need to flip my equilibrium constant by finding the reciprocal of it. And so when I calculate that, what I end up getting is 1.7 times 10 to the 33rd. Okay. Now I'm going to sum these reactions together to make sure that I don't actually need to do anything else to my equilibrium constants. My nitrogen monoxides cancel out because they're on opposite sides. My nitrogen dioxides cancel out, and what I'm left with is simply oxygen reacting with O2 to make O3. So that's the reaction that I was interested in. Now, instead of just adding these two like I did in Hess's law, I added the heats of reaction. Now here, I actually need to multiply my KEQs, my equilibrium constants. So I'm going to take 1.7 times 10 to the 33rd, and I'm going to multiply that by 1.5 times 10 to the 48th. And what I end up getting for my KEQ for this equation, for this reaction, is 2.6 times 10 to the 81st. So in the examples that I just talked about, we looked at 3 different ways of manipulating your equilibrium constant. The first one that we looked at was when a reaction is reversed. So if you reverse a reaction, your equilibrium constant is going to just be the inverse of the equilibrium constant of the original reaction, just 1 over that original value. If your reaction is multiplied by a coefficient, then the equilibrium constant is just going to be raised to a power equal to that number. So in the example, I multiplied my reaction by 2, therefore I needed to raise my equilibrium constant by 2. Finally, if I have a multi-step reaction, the equilibrium constant for the net reaction made of 2 or more steps is simply going to be the product of the equilibrium constants for those individual steps. So in the example, I flipped both of the reactions, so I found the inverse of the equilibrium constant, and then to find the equilibrium constant of the reaction I was concerned with, I simply multiplied those new equilibrium constants together. So those are the ways that you can actually manipulate your reactions and subsequently calculate your equilibrium constant after you have completed those manipulations.